Hello, and welcome back to a video series on MAC 1105 College Algebra. My name is Sean Perry. These are guided notes number 27 in the series on section 5.5, exponential and logarithmic models. The first model that we're going to be discussing is the model for compound interest. Compound interest is a kind of interest where we are paid some amount of money by, say, a financial institution, and this payment is proportional to the amount of money which is in our account. But that amount of money is then added to by this new interest. And so when do we reassess how much money we should pay into the account? The idea is that in a compounding schedule, a certain number of times per year, although it could be any time unit, it's usually in years, we will give a fraction of a percentage into that account. So this percentage is called the rate of the interest. And we will give a fraction of that. Multiplying by 1 plus this fraction is going to increase the amount principally in the account. And we are going to do that a certain number of times. We'll do that n times per year for t years. So in total, n times t is the number of times we will re-update the amount of money in the account. And when we compute all of this, we get a, the amount of money in the account. This is called a finite compounding schedule. What we are doing is picking a number of times per year to compound. If we do it once per year, n is 1, and that's annual. N is 2, goes along with biannual or semi-annual, whichever you'd prefer. 4 is quarterly, 12 is monthly, and 365 is daily, although you will find some sources still treating this as 360, the so-called banker's rule. This was done to simplify the calculations when these kinds of calculations were done by hand. Now, we also have an infinite compounding schedule. The returns that we get when we increase the compounding schedule, well, we get a little bit more each time. But the gains between going from annual to daily is quite a bit more than the gain from going from 365 to literally every moment. This is what we call infinite compounding. We take the limit of this process. Limits are something that we will cover more extensively in a course on calculus. But for now, let's just say that there is a trend. As we increase n, this amount that we will get, all other things held equal, t and r held equal, will gravitate not to infinity, but to a particular value. And this value is related to our constant e. They will announce whether or not you are using a continuous compounding schedule, or whether or not you are using a finite compounding schedule, compounding a certain number of times per year. Let's see how this looks in an example problem. This one asks us to determine how long it will take an initial investment of $10,750 to grow to $37,625 if we get 6.8% interest per year, which has been compounded monthly. From this, we need to extract the value of p, a, r, and n for our model. Then we can set up the following expression. We have 37,625 equal to 10,750 times the quantity 1 plus 0.068 over 12 to the power of 12 times t. And we're being asked to solve for t. We begin by isolating the exponential part by bringing the 10,750 over to the other side. And now we're going to want to take the log with this base. Now you can either type that base into the base part of a logarithm, or you can evaluate it, but I suggest just typing this whole expression right on into the base of the logarithm, either using the log base command or the change of base formula. Suffice it to say, this gives us something that we could calculate to get 12t. Now to get t, I just divide by 12, or multiply by a 12th, however you like it. We could type this into a calculator and evaluate t approximately. Let's see what that would look like. So I'll use the log base command. Into the base, I will put 1 plus 0.068 divided by 12. And then into the argument, I'm going to put 37,625 divided by 10,750. Closing my parentheses, we press enter, and dividing this by 12, we get our answer. Question number 32 is similar. We identify p, we identify a. They've given us a percentage, which we write as a decimal, and they've told us the compounding schedule is semi-annual. Thus, we want to set up our equation this way, divide over the principal amount to isolate the logarithm, and then take the log base that of both sides, which will free up the 2t on the right and take in an argument of 41,925 divided by 10,750 on the left. And now finishing the problem by dividing by 2, we get 27.342 and so on, which we could round to 2 decimal places as such. Question number 33 comes in 2 parts. Here they increase the interest rate and all else stays the same between the 2 of them. They ask how long it will take our principal investment of $28,000 to double, which means that the amount in question will be twice that, or $56,000. Now, actually, they didn't need to tell us the principal amount. Surprisingly enough, the amount of time it takes to double will be the same, regardless of how much money was put in there. We can see that in the first step of trying to solve this problem. All we're going to do is divide the principal from both sides. And so what we're going to do is take the log with this base of 2. Now, in case this is freaking you out that we have an expression in the logarithm space, this one is a fairly easy one to just evaluate. 0.05 divided by 2 and then add that to 1, we get 1.025. If I want to solve for t, then I need to divide by 1/2. And then we could evaluate this using the log base command, or if we had a scientific calculator, we would need to use the change of base formula and evaluate this guy here. That's going to give us 14 years approximately. On the other hand, if I wanted to use a rate of 10%, that's not going to change anything about this calculation, except for the base. 1 plus 0.1 over 2 is 1.05. And so our calculation gives us about 7.1. The next one, 34, asks us to determine how long it will take for some investment amount, $9,750, to increase by 75%. Increasing by 75% means we now have 1.75 times our principal amount. And we're asked to consider what if the rate was 13.27% and we were doing continuously compounded interest. So for this one, we're going to want to use the compound interest formula. I just wanted to note again that even if you did want to compute the A term here of 17,062.5, it's really not necessary, because what we want to know is that we've increased by a factor of 1.75. So that cancels the p's, and really it's 1.75 that we were trying to get to in the first place. And 17,062.5 was just kind of an unnecessary intermediary. The e term, or the 1 plus r over n term, is a proportion. It's what we would multiply p by in order to get a. So if I wanted to double, that proportion would have value 2. Now, taking the log of both sides, we liberate the exponent 0.127t, which is 13.27% as a decimal. Dividing by that, we find our value of t, which is 4.2 approximately. Number 35 asks us about an exponential model for population. Population growth, as long as resources are plentiful, is oftentimes an exponential function. It gives us that t is the number of years since 2020. So then when they ask what was the population in 2020, that's at t equals 0. This zeros the exponent, and e to the 0 is just 1. That lets us see that this number here is our initial population in the year 2020 if we take 2020 as our baseline. If they say t is the number of years since a certain year, that year is sort of your year 0. Then they ask, what year will this population reach 34,626? So what we want to do in that case is solve this expression for t. Dividing this initial population over, we get the factor by which that population increases to get 34626. That's going to have a value of e to the power of 0.02117 times t. Taking the log of both sides and dividing off the coefficient of t, we wind up with approximately 14 years. But remember that we were starting in 2020, and so this year would be 14 years later, or 2034. The next model we'd like to discuss is the pH scale. The pH scale is a logarithmic model. It tells us to take the logarithm of 1 over h plus, where h plus, also written as h plus in brackets, is the concentration of hydrogen ions in a solution. Whatever a hydrogen ion is not really of our concern. Neither is the meaning of moles per liter. By the way, a hydrogen ion is sort of a bare proton with no electron partner. It's a raw, single positive charge on top of a proton just floating around waiting for something to bond to. And a mole is sort of like a giant dozen, something on the order of a trillion trillion. And we're wondering how many of these things are in each liter of solution. How salty is this soup? This is a kind of density measurement. And what we're going to do is solve for this number, which indicates the density, using this expression. Or, given a density, we'll be able to find this thing called the pH by taking the logarithm of 1 over that. They tell us first that the pH of vinegar is 2.8, and they ask us what is the hydrogen ion concentration. But this is just a matter of solving this equation here. We take 2.8 and we raise both sides into the power of 10. This gives us something that I can rearrange. To solve for H+, we multiply this up here and divide this down to get 1 over 10 to the power of 2.8. 10 to the power of negative 2.8 would be a perfectly fine way to leave this, and I think that's what's acceptable as the answers in the My Open Math homework. But just to get an understanding of what that is, it is a decimal, which says that our concentration is 0.0015848 moles per liter, or approximately 1.6 times 10 to the negative 3. Next, they tell us about human tears, which has a pH of 7.4, slightly basic. What then is the hydrogen ion concentration of tears? Well, this is the same equation again. Let's solve it a slightly different way. Notice that 1 over something is that something to the negative 1 power, which we can bring out like so. This gives us another idea of pH, that the negative of that number is equal to the log of the hydrogen ion concentration. Taking 10 to the power of both sides, we wind up with 10 to the power of minus 7.4 is our hydrogen ion concentration. One could work this out, although it's probably best just to leave it in scientific notation, or in this exponential form as 10 to the negative 7.4. One thing that they didn't ask is about how we would get pH given a hydrogen ion concentration. But just keep in mind, that's no different than substituting in a value for this H+, and then seeing where the logarithm takes you by substitution. 5.5 just starts us over again immediately with questions we've already talked about, namely a population function. It asks us what was an initial population. Well, when t equals 0, we're at year 2020, so this will be 16,730 for our initial population. And then they want to know when will this population be 1,916. To get that, we want to substitute these numbers in and solve for t. Divide your coefficient over, take the natural log of both sides, and divide by the growth constant to get t. This gives us 132 approximately, and so our year will be 2,152 when Stuart achieves this population. Next, we have another question about Stuart. So I suppose this is clear at this point that these aren't real models. These are just made-up numbers. It asks us if we can find the parameters for this model, namely y0 and k, given two timestamps, a population in 2010 and a population in 2020. They say that t is the number of years after 2010. That means that our initial population is going to be the population from 2010. 14,953. On the other hand, we can solve for k in the following way. We're going to want to put 14,953 in for our initial value, divide it over, take the ln, divide by 10, and we get our value for k. They ask for it to 4 significant digits, not decimal places. I don't want to go into too much information on that because there are many rules about how to add, subtract, multiply, and divide certain numbers of significant figures and figure out how many numbers should be in your answer. What I will say is when they ask for sig figs, don't count the leading zeros here. This only has 4 significant figures, this leading 0 invisible, and these 2 in front really don't count. Once we have that, we have a model that we can use to calculate whatever we like. In this second part, they want to know the population 27 years into the future. Well, this population is already described by this equation we have nothing to solve for. So plugging in these numbers, we get 17,662. The next question asks when the population will be 20,116. Divide over our coefficient, take the ln of both sides, divide off the rate constant, and we get t. This gives us 48 years, so if t is the number of years after 2010, we just add 48 to 2010 to get 2058 for our answer for part C here. Now, the same kinds of population models that work for humans in unfettered growth will work for bacteria in unfettered growth. And whenever we go to create these models, We are sometimes given an initial population. That's a nice, easy parameter to get, is why not? And then k is the next thing we want to solve for. What we're told is that this population of Escherichia coli doubles every 16 minutes. They didn't actually even need to give us an initial amount to get this rate constant if they tell us the doubling time. That's because the initial population will be doubled on this side, and therefore these two cancel just to give us the factor of 2. Now taking ln of both sides, dividing by 16, the doubling time, we wind up with a growth constant. We can then answer these other questions, like how many bacteria will be present after 105 minutes? Well, that's actually just a matter of plugging in 105 into this equation. Then it says how long until we reach 100 million? So we take 100 million, we divide off the initial population, then we take the ln of both sides, then we divide by this rate constant to give me 281.7, or about 282. Problem number 4 asks us to calculate something else once we are given the doubling period. They told us the doubling period is 35 minutes, and that after 51 minutes, the bacterial population is this much. Notice they didn't tell us the initial population. That's actually the first question. As usual, we need to begin by calculating the rate constant. This is taking the ln of 2, dividing by 35, and using this rate constant. To find out the initial population, we have to solve for that value. This means dividing off everything over here that we do know, which is this whole exponential term. Let's just take that and divide it down into this denominator, and plugging this whole expression into a calculator, we get 16,969.05, or about 16969 approximately. The next one asks for the bacterial colony population after 4 hours, but all my previous calculations, including the rate constant, were in minutes. That means we need to translate this to minutes in order to keep all the things the same. That's 240 minutes. And if I plug in 240 into my time slot here, we have all the other things we need to calculate y, which is going to be 1,967,163.92, or approximately 1967164. The next problems begin our discussion of exponential decay as a word problem. The terminology decay refers to the decay of radioactive isotopes. These isotopes change their structure over time in a somewhat random fashion. One characteristic of these is a thing called their half-life. Similar to the doubling time of a population, the half-life is the amount of time that you have to go before half of the substance remains. The first question mentions radium-226 with a half-life of 1,600 years. It asks how many years will be required for radium-226 to be reduced to 15.7% of its original amount. These models are almost identical looking to population growth models. The only difference is that when we solve for our constant, what we will get is a negative number. In this case, taking ln of 1/2 and dividing our 1,600 to the other side, we get our constant of negative 0.000433322 and so on. Now, if I ask the question, when is this model going to be equal to 15.7% of the original amount? The original amounts cancel, and we can see again that the amount of time it takes to reduce to a certain fraction is again independent of the amount of stuff present at the beginning. What we now must do is take the ln of 0.157 and divide by the constant. Once we do that, we have solved for t, and we get that that's 4273.8, or approximately 4,274 years. These other two questions I think are a little bit confusing because they need to tell you the half-life, or at least some other piece of information, but for some reason they don't. So I think that it's prudent, if confronted with something like that, to go outside of the textbook and just Google it, right? I mean, these are actual things, right? Strontium-90 is a thing which we study, and we know its half-life very well. It turns out that this is in fact 28.8 years. So if that's true, how long would we have to wait? We begin by completing the model and calculating the rate constant. The half-life tells us the rate constant by solving this equation. ln of 1/2 divided by the half-life is going to give us that rate constant, which is negative, indicating exponential decay. If we reduce by 91.1%, there will now be 8.9% of the original remaining. and so that's what we want to write on the left-hand side. This one, they didn't even tell us the initial amount. The initial amounts will cancel, and so it's somewhat irrelevant to the problem. Now, when we solve, we're going to take ln of the 0.089, that brings this exponent down, and then dividing off the negative 0.0240676, we get our t. This t value is 100.51, or about 101 years. The next question is similar. They ask us about iodine 131. A quick Google tells us its half-life is 8 days. And they ask us how many days are required for the Fukushima disaster iodine 131 to decay to 0.6, the original amount. So we first solve for our rate constant, canceling the initial amounts. We take the ln of 1/2 and divide by the half-life. This gives us our rate constant. Be sure you're taking plenty of decimal places of the rate constant. I find 6 significant figures usually suffices, but there are ways that we could use the calculator to store more. I'll show that in a later problem. Now, how long until we have 0.6% or 0.006 of the original amount? Well, it'll be this, ln to liberate the logarithm, and dividing by the k constant, we get our time t. This turns out to round to about 59 days. Problem number 8 asks us about coffee. It says that caffeine has a half-life of 4.4 hours, and that an average cup of coffee has 101 milligrams of caffeine. Now, if we drink one, we start with 101 milligrams of caffeine in our body, and now we want to know certain facts about it. First of all, what would the rate constant be? Again, we're going to take the half-life, which was given as 4.4, take the ln of both sides, divide by 4.4, and we get our rate constant. Now they want to know how much caffeine will be left after 18 hours. Plugging things in, there's nothing to solve for. These are all constants here. We just evaluate to get about 5.9. Lastly, they ask us how long we'll have to wait before only 1.5 milligrams remains. To solve this for t, we first isolate the exponential, then take ln of both sides, then divide by negative 1.575 to get our time t. Rounding to the nearest whole number, that's 27 hours. The next one returns us to radioactive isotopes. They tell us the half-life of tritium, and we're going to use that to get K, although it is not K itself. Over here, we are asked how long will it take before the watch loses 95.9% of its brightness. They're asking us to presume that brightness is proportional to the amount of tritium present, which probably isn't a bad assumption. It also means that the amount left we have is 1 minus the reduction, which is 0.041 or 4.1% of the original. We begin by acquiring our rate constant. ln of 1/2 divided by the half-life will give us our rate constant. And now we say, when will it get us 0.041 times our original amount? Original amounts cancel. We take the ln of this proportion, we divide by the rate constant, and we find our time t. This will happen in 57 years. Carbon dating works by a similar process. They tell us the half-life of carbon is 5,730 years. And so they want to know how old some bones are that have lost a certain amount of carbon-14. First, let's solve for the rate constant given the half-life to find negative 0.001297 for K. And if we've lost 75.1%, it means that there is 24.9% remaining, or 0.249 as a decimal. We plug this in, we take the log of both sides to liberate this logarithm, we divide by our rate constant. This is going to give us 11,492.9 and so on years, or approximately 11,493. Here we have another problem involving half-life. It tells us the half-life of americium 241, which is 432.2 years. Now they tell us that after a certain number of years, the initial amount has been reduced to this amount. What was the initial amount? This is a slightly different question than last time. But we begin the same way, which is by finding the rate constant given the half-life. I'm going to stop with the initial steps. We've seen that they're the same each time. You're taking ln of 1/2 and dividing by the half-life. This gives us our rate constant K. But now we can plug that in to solve for what we get after 314 years have passed. This means solving for y naught, which means dividing this proportion over, and that gets us 189.99, or about 190 for our initial amount. Once we know these two parameters, we can plug in whatever we like. For example, after 213 years, there will be 135 milligrams in our sample. The initial amount was in milligrams. 12 doesn't even get so specific. It just says we have some radioactive goo, and it tells us not its half-life, but how much it's decayed after 150 minutes. It started at 124 grams, that's our initial amount, and then after 150 minutes, we have 15.5 grams. Can we get our rate constant from this? The answer is yes. If I know I have 15.5, and that was equal to 124 times e to the k times this t, 150 minutes, we divide by 124, we take the ln of both sides, and then we divide by 150 to get our rate constant. To find the half-life, we are asking at what time t will I have half what I started with? Notice this does not depend on the initial amount as it cancels instantly. And then it asks us to take and solve for t, which means taking the ln of both sides. Now, I noticed that when I went to go take the ln here, we got something very close to 50. And so I wondered if I had used enough decimal places. People often ask, how many decimal places do I need? And my answer is usually, well, until it stops moving around how many decimal places you want to round to. It's an operational question. It's not a question that has a simple answer. So one thing I want to note for you guys is how you can store this in the calculator. Let's say you didn't want to round at all, or you wanted to round some minimum amount, but you didn't want to spend all that time plugging in numbers. If I take ln of 15.5 and I divide that by 124, then I've taken a certain amount after 150 minutes, I divided it by the initial amount, I took the ln of that, and now I'm going to solve for k by dividing by the time, 150. And if I do this, I get my rate constant that I had before, but what I want is to store that rate constant. So we could even do this straight from the last line. When I was typing this in, I could have pressed store as, let's say, alpha k. Now, every time I say k, it will use those numbers instead. And one of the nice things about that is we can see what happens in our calculation for the half-life. If I divide by k against ln of 0.5 or ln of a half, to do that, I'll just take ln of a half and divide by k. And that gives me 50 on the nose. So the difference between the fourth decimal place here and stabilizing to the true value of 50 was not something I saw even when I took 1, 2, 3, 4, 5, 6 significant figures. If we want a lot of decimal places, we need a lot of accuracy, and this is perhaps the easiest way to get it. Just store your constants as letters in your calculator, and then you can use those wherever you see fit, including, for example, in calculations like this, where now I can just say 150 times e to the power of k, which we've stored as our constant in question, times 80. And this will be the most accurate answer that we could get because we've done the least amount of rounding for k. Alrighty, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.